3 properties of Laplace transform. So here we will see some of the properties that we already saw previously, but there are new ones included in here, and now you will see the Laplace transforms of the derivatives as well. So let f be a function where f prime, f double prime, and so on represents the derivative of the f function, and let all of these be continuous on the interval 0 to infinity, because remember that is the interval we need the function to be continuous on for finding the Laplace transform. And we denote the Laplace transform of f by uppercase f of s. Then Laplace transform of f plus g is equal to Laplace transform of f plus Laplace transform of f of g. So note here this property and the second one, if you recall, these are the combined, they make up the linearity property. Okay, the next one, Laplace transform of e to the at of into the function f is equal to the Laplace transform of f translated by a. If you recall, this uppercase f of s minus a represents the translated function to a units to the right. And if you recall, we saw that the Laplace transform of e to the at was 1 over s minus a, and Laplace transform of 1 was 1 over s. So if you notice, this is what we are saying over here in this property number 3, that this is the transform, the linear transform a units to the right of the function 1 over s. Then we have number 4, which represents the Laplace transform of the first derivative of the function f, and it is equal to s f of s minus f of 0. And I will show you later at the end of this section how to prove number 4. And we might also look at number 3. Okay, so these are the properties, and we now need to understand how to use them to compute our Laplace transforms for the given functions. So here we have first given function. Now notice here, this is the product of these two functions. And if you recall, in section 7.2, we already have a formula for that. But now it's easy. Here in this section, the formula given is easy to remember. So just recall what is the Laplace transform of sine bt. The Laplace transform of sine bt, if you recall, was b divided by s squared plus b squared. Now we have this function being multiplied by e to the minus 2s. So according to the formula number 3, the Laplace transform of the first term here will become b divided by s minus negative 2, which means s plus 2 whole square plus 4, and then plus the Laplace transform of e to the 3t times t squared. Now if you recall again, the Laplace transform of t squared is 2 factorial divided by s to the 3. So that when we multiply it by e to the 3t, formula 3 tells us that it is nothing but the Laplace transform of t squared shifted 3 unit to the right. So we can write it as 2 factorial over s minus 3 whole cube. And then plus 5, you know the Laplace transform is 5 over s. So that is our answer. Looking at the next one, g of t is equal to 1 plus e to the minus t whole squared. Well, we don't have a formula for a function like this, but you can see that doing some algebra, you can write it as 1 plus 2 e to the minus t plus 2 raised to the plus e raised to the power 2t, negative 2t, e raised to the power negative 2t. So now we will look at what is the Laplace transform of this function. So we will denote it by uppercase G of s because our function is lowercase g, so the Laplace transform will be denoted by uppercase G, which is equal to, so 1 over s plus 2 times e to the minus 1 t. So it will be 2 into 1 over s plus 1, and then plus 1 over s plus 2. Just clean it and that is our answer. Okay, number 3. Now this one is different from the previous because we have now 3 functions being multiplied, and no formula we have seen 3 functions being multiplied. Here in number 7 I see 2 functions being multiplied, but and in the previous the set of results or the set of formulas given in section 7.2, we have product of 2 functions but not 3. So how would we do this one? For this, again, we have to use a kind of a trick. We know the Laplace transform of this function. So the Laplace transform of e to the 2t cosine of 5t will be s minus 2 divided by s minus 2 whole square plus 25. Now, using the 7th formula, number 7 over here, the Laplace transform of h of t will be, so h of s will be equal to negative 1. So notice here we have a t here. So we are considering this whole thing as f, and so we can apply formula number 7. So h of s is equal to negative 1 raised to the power 1 times the derivative, first derivative, so d by ds of s minus 2 over s minus 2 whole squared plus 25. So it means we have to find the first derivative of this one. So this is equal to negative. We will call the quotient rule. It will be s minus 2 whole square plus 25 at the bottom whole square. And then on the top, s minus 2 whole square plus 25 times the derivative of s minus 2, which is 1, minus s minus 2 times the derivative of the bottom, which is 2 times s minus 2, which is equal to negative. Now note here, I will not expand everything. We will keep the s minus 2 whole square as it is, plus 25 minus 2 s minus 2 whole square. Whole thing divided by s minus 2 whole squared plus 25 whole squared, which gives me negative s minus 2 whole squared. Now there was a negative sign in the front, so I will keep that one, and then plus 25, and at the bottom we have s minus 2 whole squared plus 25 whole squared. Now will these two cancel? This quantity with this quantity, can we cancel them? Well, actually not. Why? Because remember there is a negative sign in front here. So this quantity on the top is actually 25 minus s minus 2 whole square. So we cannot do the cancellation here. So what we can do is pull out the negative sign as a factor on the top. So we have a negative sign from the formula. Then at the top we have negative of s minus 2 whole squared minus 25. And at the bottom s minus 2 whole squared plus 25 whole squared. Now this negative sign and this negative sign, they make it positive, so the final answer will be s minus 2 whole squared minus 25 at the top and s minus 2 whole squared plus 25 whole squared at the bottom. So this is the final answer. Okay, next one. So it's saying k, the function k of t is equal to t times sine square t. Now we haven't seen a Laplace transform of powers of that trig function. We have seen sine at or bt and cosine bt, but not squared. So what do? We convert it into first degree trig function. So we can write it as t times 1 minus cosine of 2t over 2t whole divided by 2, which can then be written as t over 2 minus 1/2 t cosine 2t. So now to find the Laplace transform k of s, we go to now t over 2, the Laplace transform of that one, remember. So 1/2 I can factor it out, and then the Laplace transform of t will be 1 over s squared minus 1/2 times Laplace transform of t times cosine 2t. How do we do that? Again we apply the formula number 7. So we get negative 1 raised to the power 1 times d by ds of the Laplace transform of cosine of 2t, which is s over s minus s squared plus 2 squared, so s squared plus 4. So now I have to take the derivative of that. The first term remains as it is, 1 over 2s squared minus 1/2 times the derivative of this quantity, which is s squared plus 4 whole squared, then s squared plus 4 at the top times the derivative of the top, which is 1, minus s times the derivative of s squared plus 4, which is 2s. So combining the terms, let's go on the next line. So I have first term is 1 over 2s squared minus at the bottom s squared plus 4 whole squared. In the top I get s squared plus 4 minus 2s squared. So I'm getting 4 minus s squared. So we can leave it like this. This is our answer, just 2s squared minus. And if you want, you can factor out the negative sign on the top and write it as plus s squared minus 4 over s squared plus 4 whole squared. There are a couple of more questions which we will do in the next video.